So example 6 says, there were 43 cars entered in the 2015 Daytona 500 NASCAR race. And how many different ways could first, second, and third place prizes have been awarded? So again, what am I asking myself here? The first thing that I realize is that we're talking about place. And when we're talking about place, I know that order matters. Now I need to find out what's the total. There were 43 cars total. And it looks like we're looking at first through third place, so we want or only care about the first three things. So again, a car can't repeat itself, so I know there's no repetition and order matters, so that tells me no repetition, order matters, says I'm going to be using permutations. It's always the larger number or the total first, so it's 43. I'm going to hit MPR in my calculator by hitting that PRB button and then enter. And then I'm going to enter the number 3 because I want the 3 places. And when I do 43 MPR3 in my calculator, please do so now, I'm ending up with 74,046. That's what I'd put in the answer blank. 74,000 total different ways that the first 3 cars could finish in the NASCAR race. Huge numbers. Let's go on and look at this next section. The next section kind of realizes that not always does it have to be easy. Sometimes we want to use the counting principle as well on top of permutations. This next example is really important for us to understand. It is on the test, so please make sure you pay attention. It says there are 5 women and 4 men to be seated in a row of 9 chairs. How many different seating arrangements are possible if, okay? So let's first of all talk about this. 9 here is the total. There's 9 total people. And it's a seating arrangement. Anytime you see the word arrangement, that means order matters. So if you sit in the first seat, it's different than if you sit in the second seat, okay? So let's read part A here. It says, there are no restrictions on the seating arrangements. Well, if there's no restrictions on the seating arrangements, the total that I have is 9. I want all 9 of them. Order matters. And there's no repetition. So if this is the case, this tells me that I want to use permutations. And it's always the larger number or the total first. So that's 9. And then it's how many you want, which is also 9. Another way that I could have done this in my calculator is realize that this is the exact same thing as 9 factorial because I have 9 objects and I want to arrange all of them. So either of these would work. Please put it into your calculator now. When I put this into my calculator, I seem to be getting 362,880 possible ways of arranging these 9 people if order matters. This is a stark difference between example B. Example B is a little confusing, so please try to bear with me. It says, what if the women have to sit together and the men have to sit together? So we still have 9 people, order still matters, but we need to group the 4 men together and we need to group the 5 women together. So how could they sit? Well, let's think about those 9 seats. I could group the women together, and then I could group the men together. Well, how many women total are there? Well, it seems there's 5 women, and how many of them do I want to organize? All 5 of them. Again, I could have put 5 factorial here if that's what I wanted. And then I look at how many men were there. Well, there's 4 total men. I want to arrange, order matters, no repetition, all 4 of them. The fundamental counting principle says, though I pick the women, I pick the men, and then I multiply those 2 together. So either put 5 MPR5 times 4 MPR4, or put 5 factorial times 4 factorial. Let's see what you get in your calculator. I seem to be getting 2,880. That's where most people would stop right there. But here's the issue. If I put the women first, this would be like the women took seats 1 through 5, and the men took seats 6 through 9. Couldn't have I done this the other direction? Couldn't have I done it where the men went first and took seats 1 through 5, and then the women went second and took seats 6 through 9? Again, it would be the same number. I have 4 men and I want to arrange all 4 of them. I have 5 women, and I want to arrange all 5 of them. So that would again be 2,880. But that would be with the men first and the women second. So what do I do with those two numbers? Add them together, 2,880 plus 2,880, or I could have just multiplied my result times 2, and I get a total of 5,760. Again, the most typical mistake here is that they would have stopped at 2,880. You have to remember to swap the order of the two. So group the women together, group the men together, and then swap the order, or just multiply it times 2. Okay, so let's look at this next example to kind of emphasize this. It says there are 7 tutors, 3 juniors and 4 seniors, who must be assigned to 7 hours at the Mass Center is open each day. If each tutor works 1 hour per day, so no repetition, how many different tutoring schedules are possible if? All right, so again, we have 7 is my total. And I do know that it's a schedule. Because it's a schedule, I do know that order matters. Because order matters, there's no repetition. I know that I'm using permutations. I'm going to be using permutations. So, if I have 7 hours, I have 7 tutors. How many do I have? My total is 7. How many do I want? I want 7. Again, here I could have put 7 factorial. 7p7, put that into your calculator. I'm ending up with 5,040 total possible ways of organizing just those 7 tutors in those 7 hours. It's amazing how many that is. But let's look at this next one. It says if the juniors tutor during the first 3 hours and the seniors during the last 4, how many do I have? So this is similar to the previous problem. I've got to think about my juniors first and my seniors second. How many juniors are there? There's 3. How many do I want to organize? All 3 of them. How many seniors are there? 4. How many do I want to organize? All 4 of them. What do? I multiply those two numbers together. So when I do that, please do so in your calculator now. I'm getting a total of 144. So the difference between this problem and the previous problem is we don't need to consider juniors, then seniors, and then swap the order and do seniors, then juniors, like we did with men and women, because it very specifically tells us juniors have to go first and seniors have to go last. So this is way, way different. If we force when they have to go, it's far fewer examples. I'm ending up with 144.